Good morning. Welcome to the class ECE451, the control engineering. Last time we have discussed the stability of a system, and we introduced several different ways to check the stability. Right? We can check the location of the poles, or we use a table method, the rules table. Right? So we have different way to find the stability of a system. Today we keep working on this, but we focus on feedback system. Last time we just considered in generally any kind of system, right? So today we focus on the feedback system. Okay, the ECE451. So this class is for what? Okay, I leave this blank. I will put it later. I need to turn around. Sorry. Okay. So what is a feedback system? Firstly, right? Feedback system is generally looks like this. We have a plant. You can see this is kind of a machine here, a device here. You want to control this one. How to control it? You add a controller. This is a controller. And you need a feedback. Here's the input. Here's the output. The plus, usually here's a minus. And we consider more general case. So here maybe you have some kind of a noise or disturb. So like I have a B of S here, and I have a W1 of S. W1 of S. This W1 of S is a kind of a noise or disturb or whatever, right? And if you want to consider more complex case, here you can have another W2 of T. Yeah, if you write in the S domain, there's a W of S, W2T. This is also a noise. This noise go to the sensor. This is sensor. Yeah. And here's a plant. And this is the controller. So this noise go to the sensor. This noise go to the plant. But in most cases, you just think W2 is part of W1, right? W2 go to here. You have H of S times W2 of S, right? Now of course you also have Y. So here's this one plus Y. And this go to here. This one subtract this one, then go to here. So this part, the part related with W2, finally go to here. So you can also think W2 is go from this way. Of course, the gain is different. Here W2 need a H, need a -1, need a DS. So when W go to here, it will be W2 of S times H of S times D of S with a negative is here. And if you consider W2 is coming from here, you can think this is a minus, this is a D of S, H of S over that B of S times W2. You think this one together with W1 go to here. Right. So in most cases we do not discuss this part. We just think there is only one noise coming from here. Only one noise coming from here. We can suppose W2 is always 0. Now we just think it's more similar. So this is a feedback system. Feedback control system. Of course, you can also consider a control system without the feedback. Without the feedback, then that will be things look like this. You have D of S is a controller, and the G of S is a plant. That's it. And of course, here you also consider you have some noise disturb here. W of S, W of T, W of T. Here's input, here's output. So for this is a, we call this is open loop system. Open loop system, and this is a closed loop system. Closed loop system. Now it's just a name, makes sense, right? This you have loop. Here's a no loop. The loop is open. Loop is open. Okay. Okay. Then for the control system, we have several topics we need to consider. The first one is a stability, right? Topics. I will say the basic topics. The basic topics. The first one, the stability. G of S itself may stable, may not. That depending on the system, right? Depending on the model. Some physical or electrical device, maybe it is stable, maybe not. And our problem is we want to add a D at a controller, and also needed the sensor to make the system stable. So this is for stability. If you use the feedback control system, then you can do some work, right? And if you use the open loop system, you can also do the similar thing. But how to do it? I think we have example about this kind of thing, right? Suppose this is a K, we try to solve to find which K can make the whole system stable. We have some homework and examples, or I will even have one in the first exam, right? One problem in the first exam. So we are working like that. We try to find the controller, make the whole system stable. And for the open loop, we can also do these kind of things. So how to do it? For open loop system, we choose D, the DS, to cancel the poles of G of S in the right half plane. Right half plane. Right. If there are any poles, if there are any poles in the right half plane, we need times G times D in front of G to cancel them. Yeah, that makes sense, right? You have a pole, then you just time here you put a 0, then they cancel, then they will be fine. But by this way we have several issues here. The first one, you cannot make this part stable. You know, if G is unstable, then some noise may cause the system give output is unbounded. The output will go to infinity, right? So you use DS here. You can cancel these poles, but before this D is here, so this D only work for input R. For the noise, the D do nothing. So if input, if the noise, certain kind of noise can still make the system give a kind of unstable behavior, right? So this is one problem. This is for open loop, yeah. To this one, W2YT is still unstable. It's still unstable. And suppose the G of S is unstable. Then you add no matter what is the D of S. This one is still unstable. Secondly, you want to cancel the pole, right? Cancel the pole. To cancel the pole, to cancel the pole, oh, I need it. To cancel the pole, you need D of S has exactly same zero with this pole. But if you have a little bit arrow, no matter how much it is, just the arrow, small arrow, very small arrow, then the pole will be still there. Only if the zeros is exactly equal to this pole. The zero here is exactly equal to this pole. That is very hard, very hard. To cancel it, we need a zero in D of S equal to that pole without any arrow. Without any arrow, or in most cases we can't. We cannot do that. We can't find it. You almost cannot do it. You always have a little bit less or more. You have some arrow, then the cancellation will be failed. So for this kind of system, it's very hard to make the system stable, I would say. Mathematically you can do it, but if you want to build some machine use this way, it's very hard. Because the pole, there's some arrow, even in both sides, D and G, you have some arrow, and even when you are running the system, the real system, the parameter maybe change a little bit when it's running. Like the circumstance, like the temperature of the air will cause something different in the system, right? Then you will lost the stability. So this is very hard. So this is a kind of good point. Good point of feedback system. Feedback system. Usually we have an interval to make the system stable. So you have an interval. Interval, that means you have a small arrow, doesn't matter, right? It's still inside the interval. So small arrow is also fine. Even you have small arrow, it's also inside that interval. Right? So this is one good point for feedback. When we consider the stability, we know the closed loop were better than the open loop. So this is one of the reasons, almost the only reason, not only, but the most important reason. People like use feedback system, not rather than just open loop control system. Right. So this is the first one about the stability. And the second topic, basic topic 1 is stability. The second one, as I told, the system maybe have some error, right? So we call this sensitivity. what is sensitivity? We suppose the plant G of S is G of S with some theta a parameter. Maybe change. This is a parameter may change. So if set change, what will happen? What will happen on the on G of S and okay, I need a name for the overall transfer function. Overall transfer function on this y of S over r of S, right? Y over r, the overall transfer function. I denoted it as a transfer function, right? Denoted it as transfer function, so just T of S, right? T of S. So what will happen on G of S and T of S? You can think like the good case is a small change on the theta, then will cause a little bit change on T and G. Right. And another side is not so good, is a small change on theta will cause large difference on T or G. Right. So this is a sensitivity, and we denote like this: sensitivity of a transfer function with parameter theta. It is writing this way: dt over t, and here's a d theta over theta. Yeah, right this way. This is a percentage change, right? Percentage change on t, and this is a percentage on theta. So we check the ratio between them. If this is small, that means if you have some change on theta, then the change on t were even smaller than the change on theta. Right? If this is a number larger than 1, then it kind of increase the change. The small change on theta will cause a large change on t. Right? So we calculate like this one. This is the sensitivity of this transfer function related with parameter theta. So here actually we have two things. The considered thing is S T of S theta and S G S of theta. We want this one smaller. We want it smaller than this one. I want this one smaller than this one. So this is a sensitivity. We can do a calculation. Example. What is sensitive? Right? Example. We consider G of S, which is simply just 1 over S squared plus beta S. Beta is a parameter. This is a plan. And the system, okay, it's a feedback system, but this is the most simple case. Just the G go back, plus minus, okay, just like this. That means the controller, here is still a controller. The controller, it is just 1. Right? Controller is do nothing. And also we have a sensor. The sensor is also do nothing. Okay. Then T, we have two sensitive. The sensitivity of G according to this set. So this one equal to dg over G and d set over set. So this is actually dg over d set times set over G. Alright, now we plug in. Oh, set is beta. Set is beta. Now set is beta. So this is a G beta, where dg over d beta. Take derivative on this, on beta. So this is a fraction. That will be numerator is 1. So this is a negative s squared plus beta s squared. Numerator is 1 times this one. Take derivative on beta. I have s. Right. So we have this one. And times set divided by G is 1 over s squared plus beta s, like this. Okay, we can do some simplify. This square can be cancelled with these, so the final answer is negative s set over s squared plus beta s. So this is the sensitive. It's still a function of s. Right, function of s. Alright. And we want another sensitivity T of s, the overall transfer function. T of s. We want the sensitivity of T of s according to set. Then similar thing, we check dt over t and d set over set. So this time is dt over d set. The set is beta. I confused. This is a theta is a theta is a beta. Theta is a beta. Sorry, theta is a beta. That's a beta. Times beta over t. Right, beta over t. And okay, when you know what is a t. T equal to. It is now we can use the gain formula, right? We have one forward pass, that is a G, and only one loop, so denominator is 1 minus that loop. That loop is negative times G, right? Negative G, so here's a plus. And for numerator, I still need a delta 1, but now delta 1 is just 1. Make sense? Delta 1 is just 1. 1 minus all the loops do not touch the path, but now only loop touch the path, so we don't need that. Okay, T is this one, which is 1 over s squared plus beta s. This is a numerator, and denominator is 1 plus 1 over s squared plus beta s. So this equal to I times s squared plus beta s on both numerator and the denominator. So we have this. This is T of s. Alright, with this T of s, so the sensitivity of T according to set is the derivative of these according to beta, that is a negative s over s squared plus beta s plus 1 squared. Right? Yeah, similar with this one. And times beta over t. Beta is beta over t, 1 over s squared plus beta s plus 1. And similar, we can cancel these. I get negative s beta, same with that in the numerator. And denominator is s squared plus beta s plus 1. Okay, so we know the sensitivity of t according to theta is this one. And if you want to compare these two, you compare the G sensitive of G with beta and the sensitivity of T with beta with theta. Sorry, confused. I confused by myself. Theta and beta, same thing, huh? All right. Compare. We can just like as set G over S with that state with that bait T, it will be G is here. Now G is this one, S squared plus beta S in the denominator. So this one according S squared plus beta S in the denominator, and this one over these. So now this one we're going up. So S squared plus beta S plus 1. So it is 1 plus S squared plus beta S. Here's 1. Now we have this. We have this one. You will consider the bait. You choose the bait. Make this large. Make this large. Then that means this small, right? To make this large, then this will be small. This will be small, right? So yeah. So you can choose different bait. You can know which kind of bait. Some bait that were located in the place the denominator is large. That means the whole thing this is small. Then that bait is not good. Too sensitive, right? You will choose bait. Make this fraction large. Well, this is the function of S. When S different, this value will be different. But I think you can find a certain value of bait nearby that bait. This one will be, it is a function, but it will be larger than a certain value. Things like that, right? The function might be looks like this, but it is larger than this value, right? Larger than this value. Yeah, things like that. Okay, so this is the sensitivity. So here you should remember what is the sensitivity. The definition just this one. Sensitivity just this one. Definition this one. So when a system is given, you know how to calculate it. How to calculate what is the system, what is the parameter, then you can calculate. Alright. And of course, why do we calculate these? Because we need to do a compare. We need to compare with T and G. We want to choose a bait, make these T's better, right? Yeah. Okay. So this is the sensitivity. Then the third question, third basic issue for the feedback system. Not just for feedback system, for control system, right? Control system. You need a control system. The third one is we'll call this as tracking problem. We have input for system, right? To a system. I use T. T means the overall system. The system itself might be is a feedback system or maybe more complex, right? I just use TS for the overall transfer function. Now we have output. In most cases, we want the output equal to the input. For example, you have a temperature control system, right? You need to control some temperature inside the building, or you have some device in the industry. You want to control the temperature. Then you will set the input. For example, you set the temperature as 80 degrees. So 80 is your input. And what do you want? You want the output is also 80. So the aim for you is you want these two same. You want R and Y are same, right? And so we want to know, we call this, it's a check the arrow between these two. I said it's a E of T. E of T. E of T, I use R minus Y or Y minus R. As R minus Y really. Yeah. Check E of T, which is R minus Y. We want E of T tend to be 0 when T go to infinity. We want this. We want this. Right. In the beginning, when time is small, usually it's hard to have this. But at least you hope After a certain time of running, the output of system can reach your input. We call this as a reference. Reference signal. So actually, reference signal, it is also a control signal. Right? It is also an input signal. Right? Different name, but most cases we think it's a reference signal. Reference signal. Right. So the tracking problem is like in the feedback system, you will choose controller. In a feedback system, and not just feedback, in control system. In control system, you need to choose the controller to make limited t go to infinite e of t equal to 0. Yeah, this is what do we want? We want this. If we want this, but sometimes we can have, but sometimes we cannot. That depending on the system. Depending on the system, we call this is a tracking problem. And we have type. Actually, this problem depending what is R of t. What is R of t? Type. We call this type of a system. In tracking problem, we have a type. It is a number. It is a number. Let's say like M. This M satisfies two conditions. A. If input is t to the k is a number smaller than m, then that e, we call this as ESS, steady state error. Steady state error is error, steady state error. So then the steady state error equal to 0. So you give an input. If the input is somehow a polynomial with order no more than m, is smaller than m, then the steady state error is 0. And the B, if input is t to the k and the k is larger than m, then this one will go to infinite. Make sense? This is kind of ability of the tracking, right? The system can, you can think you have this as reference. You want the output follow this R of t. Track, update, follow it. If the arrow tend to be 0 when time go to infinite, that means y of t can reach it, right? Follow and finally reach it. Yeah, follow and close to close and finally reach it. And in this case, it's infinite. That means can follow. The distance will become longer and longer. The distance will be longer, finally go to infinite. The difference between r and y will be larger and larger, and finally go to infinite. So the system cannot track. Okay, then we have a bound between those small k and the large k. That m, it is a type. It's a type of the system in tracking problem. Tracking type. You can also do tracking type. Yeah. Make sense? You can imagine, the t. When the power of k go to larger, then the input will increase more rapidly, and then the system cannot follow it. Right? This one is wrong. The input increase too fast. The system cannot follow it. Right? For large k, and for small k, okay, it's fine. The system can follow it. The input side increasing, but the speed of increase is not so fast. So the system can follow it. And we have the bond between these two, that is M. We call this M as the type, the tracking type of the system. Okay. We can have a look. We check an example. We still consider a feedback system. Just unit feedback. Alright. A unit feedback system. I suppose this is minus, this is plus. Input is R, Y is the output, and G of S equal to like S force times S plus 2, 1. Okay. So you see, actually this is a marginal stable system, right? It's a poles here and here. It's a marginal stable. Marginal stable, that means for some input it is stable, it is a bounded output, but some other input you will give output to go to infinite, right? Okay. Now the TS is G over 1 plus G, which is S force times S plus 2 plus 1. Numerator is just 1. Okay, so this is T of S. We want to check the type of T of S for checking problem. Suppose input is R of T equal to T to the I use the same notation, T to the K. Of course we suppose T is positive, negative side doesn't matter. T to the K, then we have R of S will be something here is S to the K plus 1. Here I need a coefficient. What is that? That's K factorial of K or factorial of K plus 1. I can't remember. You have table, you can check it. Alright. I put some alpha here. Alright. Alpha is constant. Check table to find alpha. Alright. Yeah. So this is R of S. So we have E of S. Now we want E. We want E is R minus Y. So we find Y first. Y of S is T of S times R of S. The input is transfer function. So we have the output. This is TS is 1 over S force times S plus 2 plus 1, and R is R over S K plus 1. Okay, this is a Y of S. And then E of S is a R minus Y. Right? E is R minus Y. So we work in the frequency domain firstly, in the S domain firstly. So we have E of S, which is R minus Y. Okay, so this R, okay, R, this is T over T times R, so it is R times 1 minus T. Yeah, this makes simple. Anyway, yeah, some calculation you can also just plug in, is also fine. This is R is R over SK plus 1, and 1 minus it. 1 minus 1 over S force S plus 2 plus 1. So this is a R sk plus 1. This is a s force s plus 2 plus 1. Here's s force s plus 2 minus 1, right? Plus 1 minus 1, so it's cancelled. Plus 1 minus 1. Alright. This is E of S. Then what is the E of T? Oh, here you will see, if you want to find all of the T, you need the inverse Laplace transform of E of S. It is this one. But now we only need this one. Limit when T go to infinite, E of T. This is ESS. We only need this, ESS. And what is this one? We have a property for the Laplace transform. This equal to limit S tend to be 0, S times E of S. You check the table of Laplace transform. Laplace transform. Yeah, you can find this formula. The final value function, final value formula, right? Okay, so we can have, now we just plug in the E of S. So this one equal to S times it. So I can cancel 1 of S, right? So it's R over S to the K. That S cancel with this 1. And times S force times S plus 2 plus 1. And here's S force, S plus 2. And the limit. Yeah, I forgot limit. Limit S tend to be 0. Alright, what is this? You see this part? This part, it is always the limit will be 1, right? And this part, where limit will be 2, 1 and 2. And this alpha is a fixed number, and so I can move it out. This is a 2 alpha times limit S tend to be 0. This is a S force over S case. Alright, we have different cases for different K. If K is smaller than 4, so you will cancel K's. You still have some S in the top, so the limit is 0. ESS is 0. Right. If K equal to 4, then the ESS is 2 alpha. Right, 2 alpha. Limit is 2 alpha. This is cancel 1, just 1, right? If K is larger than 4, this time is 0, is infinite, right? S force cancelled, but in denominator you still have some S. So it is 2 alpha over that S. S tend to 0. So it's infinite, right? Infinite. 2 alpha over 0. Right? It's infinite. You see? Now we know the type. This is a tracking type. Of T of S is 4. We have the tracking type. It is 4. Alright. Yeah. It's 4. When the input side the power is smaller than 4, the static arrow is 0. And when it's large, that is infinite. So in this case, the system can follow the reference. Finally reach the reference. And if K is larger than 4, can follow. Finally lost, right? The output is leave the reference far away. And when K is 4, here we have a fixed number 2 alpha. What does that mean? The output cannot reach the input, cannot reach the reference, but it still follow it. They follow it with a fixed distance 2 alpha. Fixed distance 2 alpha, right? The reference go, the output is also go with the same speed, but there's a fixed distance 2 alpha, right? Cannot reach. This one can reach, this one cannot reach. This is a followed. Alright. So this is one example. In the textbook, they have some formulas for some special case, like for the system with type 0, type 1, type 2, type 3. They have some formulas according to their cases. If you, I suggest you go over that part, and you can make a note, make a summary about those. Here I just gave you the general idea about it. What is a tracking type? What is tracking type? You use a different kind of polynomial input. You use them as a reference. You check the steady state arrow of the output, and then you can determine the type, the tracking type. Okay, so this is for tracking problem. The third problem, tracking problem, and the fourth, totally we have fourth problem. Fourth problem is related with that arrow, with that noise. Right? I said here we consider the system we have noise. Then this noise will cause some trouble, right? You will think, okay, maybe make the output will not be the output that you want. You want that output is something, but because the input, because the noise, the disturb, the output change. So here we hope the system can cancel kind of disturb, can cancel this noise. That will be great, right? So here we have we call this the regulation problem. Now I give the graph, looks like this. We have a system, feedback system with input R and the controller D, and here we have some noise. Noise is a W, and here's a plant, and output is Y, and we have a feedback. Suppose just a unit feedback. Alright, unit feedback. If you want to consider the sensor edge here, similar thing, just when you write the transfer function, that will be a little bit complex. Okay, then we want Y close to the reference, but because this noise, the reference is maybe you cannot reach the reference, right? So we want this. Here's I still use E for arrow. This is different with previous problem. Okay, I call this is also E of t. We want the limit of E of t when t go to infinite. This one is 0. This is what do we want, right? We want this turn to be smaller. We want this arrow will be small. That will be good. Small, that will be good. Right. Of course, this is in the case the steady arrow is already 0. The tracking type is just the Y already can track the reference. Now we have a B here. We want these to be smaller. We can have another way, or we say this one, D of S, G of S. We have a Y, right? We have this system, plus and minus, and here's the noise. We want Y tend to be 0. Y of t equal to 0. And here we suppose R is nothing, no input. R is 0. We want this. Okay, so both cases Yeah, both description the same topic actually. We want some small output caused by this disturb. You have something disturb you, and you want this one will not really disturb you. You want this tend to be smaller. You want this tend to be smaller. All right. So here we have similar thing. We have the type. We have the regulation type. Regulation type. It is a number. I still use M. Alright. It's a number M. If the noise, now it's a noise, Wt equal to T to the K, and the K is a number smaller than M. Now we have this one. Then that is also ESS. This is also ESS. Right? This is also ESS, but a different way the tracking problem. This is a ESS, steady state error, for the regulation problem. We want the ESS tend to be 0. If noise is this one, the ESS is 0. Yeah, there's a limit. Limit S tend to be T tend to be infinite at E of T equal to this. Okay. Here's one is positive, one is minus. Yeah. And B, if the noise Wt equal to Tk with K larger than M, this limit E of T is infinite. Yeah, we have these two. With these two, we say this M is a regulation type of the system. It's quite similar with the tracking type. Just you can imagine the input is here, right? Input is here, output is here, and this one is nothing. Okay. We writing this way. If we writing this way, when R is 0, this one is 0 minus y. 0 minus y, right? 0 minus y is negative y. If you writing this way, it is just y. But no, this one is 0, right? This one 0, then this one is y. So these two description, you have a different sign. This is positive, this is negative, right? This is negative, this is positive. Yeah, but you want to check whether it's 0 or infinite. That's the same thing. When I put the infinite here without the plus, without the positive, that means any kind of large number. In the negative side is large, or in the positive side are large. Right? Both are large number. Large go to infinite. Right? Okay, let's work by example. We still consider a feedback system. Actually, this is a problem just for feedback system, right? Just for feedback system. If it is a system without feedback, this is also, you can also consider, but we cannot work in this way, right? You can also consider this problem if without this feedback. Yeah, but now we just work on the feedback case. I choose a G. Let me choose a G, and suppose no D. Yeah, I just use the simple case. This is a G of S plus minus, and the noise is here. W, W, and the B is 1, B is 1, D is 1. Okay, you consider this, and the G of S equal to what kind of things can I choose? I choose s squared. Oh, I think I can use which kind of things as an example. Do I have? Oh, sorry. I think I write something before the class, but what it is? I use sorry, I lost it. I put it somewhere. Okay, this one. This one, S cube. You still use S cube. I can use S cube equal to this, S cube over S cube plus 2S plus 1. Use this one. So this is G of S. This is G of S. And I want to know the regulation type. Of T of S. The overall system, the T of S. Okay. Overall system. Now we need to consider what? We need to consider from W to Y, right? From W to Y, you consider R is 0. Input is 0. You consider W and Y. So here, now use Y of S over W of S. We use this one. This one equal to what? We still use gain formula. We have one forward pass with gain just G, right? And the third one should be 1, right? Only one loop, and the loop touch the pass, so we do not use any loop in the numerator. And the denominator is 1 minus that loop. That loop is G, right? And here is a negative, so it's a negative G minus negative G, the plus G. Okay, so this one. And then we do some simplify to find what is this one. It is G is S cube over S cube plus 2S plus 1. And numerator is 1 plus S cube over S cube plus 2S plus 1. So this is S cube over S cube plus 2S plus 1 plus S cube. So it is S cube over 2S cube plus 2S plus 1. So this is the transfer function from W to Y. From W to Y. I give a notation. I write this as T1 of S. Alright, T1 of S. Then we want the output tend to be 0. Right? I use this one. I use this one. I want this output tend to be 0. So Y of S is T1 of S times W of S. And W of T equal to T to the K. T to the K. T to the K. So WS will be that R over S to the K plus 1. So this is T1 is S cube over 2S cube plus 2S plus 1 times R over SK plus 1. So it is R over 2S cube plus 2S plus 1. Here's a 1 over SK minus 2. Am I good? Yeah. Okay. So we have this. This is Y of S. Then limit Y T go to infinite. Y of T will be limit S go to 0. S times Y of S. So you look at here. S tend to be 0, then this part will be just R over 1, right? And the limit S times this. So S tend to be 0. Here's S times this. You cancel one more. So here's K minus 3, right? You get this one. And what is this value? depending on the k. When k is large, oh, this one I get the reverse way, huh? When k is large, this is 0. When k is large, this is 0. When k is small, so my system is strange. My system is strange. Let me see. My system S tend to be 0, right? S tend to be 0. Okay. If k smaller than 3, oh, it's good. Yeah. If k is smaller than 3, then k minus 3 was smaller than 0. So 1 over sk minus 3 or equal to, this is negative power in denominator. So actually this is s3 minus k, right? This is positive. 3 minus k is positive. And s tend to be 0, this will tend to be 0. Okay. And if k is larger than 3, then k minus 3 is positive. Then 1 over sk minus 3 will equal to like some 1 over 0 that go to, right, when s go to 0. So this is infinite. Yeah, this is ESS is 0. This is ESS is infinite. Okay, the type should be 3, right? Type is 3. And when k is 3, equal to 3, then I have ESS is just, this is 3, so it's cancelled, right? S to 0 is 1. So this is R. Yeah. So we know the regulation type. Regulation type is 3. Is 3. Yeah, for this system. Right? Regulation type is 3. So if the noise is a polynomial kind of noise, the polynomial's order no more than 3 is 0 or 1, and not equal to 3. Equal to 3, you will have some kind of error here. If it is smaller than 3, then the noise will be cancelled finally. Right. So when the system runs with enough time, the noise will tend to be 0. The steady error of the noise, it is a kind of 0, right? When t go to infinite, t go to infinite, this error will tend to be 0. All right. Yeah. So this is for the regulation type. All right. Okay. So for the basic topic, basic topic for a control system, we will just look like this. Right? Just look like this. Okay. This is then what errors I can give today. Oh, today I'm run somehow faster. That's all for today I want to give you. But I only use how many times? 63 minutes. I have 10 more minutes. This is a problem for the online teach. If now we are in the classroom, I can ask you, and do you have any question? Maybe we can have discuss. If you think I'm too fast, some step is not so clearly, I can explain. But now I can do nothing. Okay, so just as it so far. So that's all for today. All right, and if you have any question, you go to the my office hour. That will be Monday afternoon from 4 o'clock to 5 o'clock. You go to the Zoom. This is one way to ask me a question. And another way is you can you can go to the Piazza. You go to Piazza. You can leave your problem in the Piazza, and when I see it, I can give you the answer. All right. So today, just like this. All right. Yeah. Sorry for that. I think maybe I'm too fast. I write too fast, or I talk too fast, or maybe I can give you more example. Anyway, yeah. So that's all for today. See you next time. Bye bye.